The size of the cache is small compared to the main memory. Therefore, there should be some mechanism to fill the data in the cache. And here we'll be using mapping techniques. There are three, in that the first and the easy one is a direct mapping. In direct mapping, the logic is each memory block maps with exactly one cache line. Something like this. To have a better understanding, let me give you an example. Imagine our system has a main memory of size 128 bytes and cache size 32 bytes. And the size of the block in main memory as well as in the cache is same. And for convenience, let me draw it separately. And the block size is 8 bytes. Now from this data, we can calculate the number of blocks and the number of cache lines. So let's do it. Number of blocks is memory size by block size. So 128 by 8, it is 16 blocks. That can be written as 2 power 4 blocks. So we need 4 bits for block indexing. Block index is 4. And the block indices are 0000, 0001. So these are the block index. Similarly, I can find the number of lines. It is cache size by block size. So 32 by 8, that is 4 lines. Or we can write this as 2 power 2 lines. So we need 2 bits for cache index. And the indices are 00, 01, 10, 11. This is the cache index. In direct mapping, the logic is the block index least significant bits are matched with cache index. So here cache index we have 2 bits, so 00. So in the block index, go to the least significant 2 bits. So wherever 00 is there, just mark them. So it's here, here. There will be 2 more positions, that is, this is actually 0, this is 4, and this is 8, and this is 12. So these blocks having the least significant bits same as the cache index, they can be placed in the line 0. So line 0 can hold 0, 4, 8 and 12. Let me redraw this. Okay, this looks better. So line 0 can hold 0, 4, 8 and 12. Now how about line 1? Just think about it. Line 1 can hold 1, 5, 9 and 13. The reason is these blocks least significant bits match with the cache index. Does it mean that all the 4 blocks are placed into it? No. This line, the line 1, can hold any one of this. Now which one it will hold? It really depends. Now the CPU must have a mechanism to understand which out of these 4 blocks are residing in the line 1. Let me take the previous slide. So line 0 can hold 0, 4, 8 and 12. For the CPU to understand which block is there in the cache, it maintains some extra information bits called as tag bits. So for each line, the CPU holds tag bits. The tag bit size is block index minus cache index. Here cache index we have 2 bits and for block index we have 4 bits. So tag size will be 4 minus 2, 2 bits. So we need 2 bits for each line. And tags hold most significant bits of block index. What it means is, suppose block 0 is loaded into the line 0. Here the most significant bits are 0, 0. So tag will hold 0 and 0. And suppose block 4 is loaded onto line 0. Here the most significant 2 bits are 0, 1. So tag will be 0, 1. And if it's block 12 into line 0, most significant bits are 1, 1. So tag will be 1, 1. Here you can notice the most significant 2 bits are different for 4 of the blocks. So this distinction helps us to identify which among these blocks is actually placed in the cache. Now let's look from processor perspective to understand how it decodes an address. For this, let's assume cache is half filled with some data and the CPU is generating requests in a sequence. These are the requests. In the previous lecture, we have covered memory and cache basic formulae. Using that, I can write the following. Memory size is 128 bytes. That's 2 power 7. So 7 bits are needed for physical address. Cache size is 32 bytes. That's 2 power 5. So 5 bits are needed for cache address. And block size, here I forgot to mention, block, let's take it as 8 bytes. So block size 8 bytes. 8 is 2 power 3. So we need 3 bits for block offset. Now let's draw the diagram. Physical address is 7 bits. So in that block offset is 3. So first 3 bits will be the block offset. And rest of the bits are block index. Here in this case it will be 4. And we know that cache address we have 5 bits. So least significant 5 bits will be taken as cache address. So in that cache addressing, the first 3 bits will remain same, block offset or line offset, which is 3. And the rest of the bits in the cache address is cache index. In this case it is 2. And the most significant 2 bits are the tag bits. Here one thing to note, to find the tag bits, we can do it in 2 ways. Tag bits equals, look at this, this is the physical address. Tag bits can be thought as physical address bits minus cache address bits. So from this, if we remove this, the leftover is your tag bits. That is method 1. Or from block index, I can remove the cache index. Still I will get the tag bits. Or the second formula is block index minus cache index. So whichever is convenient for you, you can follow that approach. Alright, this is a complete categorization of physical address and direct mapping, but this is very much messy. So let me redraw it. Okay, so in the physical address, first few bits are block offset, next is the cache indexing or the line number, and the last is tag bits. Now let's take the first request. It is 000010. If this is a request from the CPU, the first 3 bits are block offset. The next 2 is the cache index or the line number. So the line number is 00. So this is the line. So CPU is able to identify which line. Then in the physical address, the tag bit says 00, and in the directory, the tag bits are 00. Using comparator, these two are compared, and here in this case, they match. That means that the block we are searching for is present in the cache. Now using the block offset, it will go inside the block and then it will identify the exact block position. Here, whenever CPU finds the data inside the cache, it is called as a cache hit. If not, it's a miss. And for the first request, it is a hit. Now look at the second one. Again, the first 3 bits are block offset. Leave that. The next 2 bits are cache index. Here cache index is 01. That means line 1. Now for the line 1, it goes to the tag directory and it compares with the tags in the physical address. Again in this case, these two match. That means that data is available in the cache. So using the block offset, it goes inside the block. It goes to exact position and retrieves the data. Again for the second request, it is a hit because the data is available. Now here we have the third one. Again the first 3 bits are block offset. We can leave them. Directly go to the cache index. Here it is 00. So go to the line 00. Now compare the tag bits in the directory with the tag bits in the physical address. We see that here it is 00, here it is 01. It means that the data which we are searching for is not available in the cache. Therefore, this is a miss. Now what will happen? Now the CPU has to search in the main memory, find out the block, and then bring it to the cache. Now to identify the block in the main memory, it again uses the physical address. So 0100 011. So We already know in physical address, first 3 bits, in this case it is block offset. The rest of the bits are your block index. So go to this particular block 0100. So where is 0100? So this is the block. So this particular block has to be transferred here. Now whenever this happens, automatically the most significant bits will be changed. So this will change, it will become 01. And here we have B4. Alright. Now let's go to the last request. This is first 3 bits are block offset, we leave them. Next 2 bits are cache index, it is 01. So go to 01, then compare the tag directory bits with the physical address tag bits. Now here we see that they match, therefore this is a hit. That's how the CPU will operate with the data. So whenever data is not found in the cache, it will go to the main memory, then pulls the data into the cache. If data is found, it's a hit. If data is not found, it is a miss.